All right, so the solubility rules that I asked you to pull up, so I'll pull them up right here. Um, if something is soluble in a solution, its state of matter is aqueous. And the reason it's aqueous is because we're going to consider that our solvent for all of these problems is water. All right. And that's just because it's the most readily available. So what we have are what are these called these solubility rules. Now these are for ionic compounds. These are not for like carbon dioxide, like all of our nonmetals. It's not for ionic. That's metals with nonmetals or metals with polyatomic ions. Okay. Um, so you can see, right, we have soluble compounds. Now, if something is soluble, it is considered, comment on here, aqueous. AQ is the letter, or is the symbol for aqueous. So, right, we have states of matter. Solid is a pretty common state of matter you're aware of. It's a solid chunk, right? Fixed position. That's what it means to be solid. Okay. A gas, okay, is stuff that's spread really far apart. Um, gases are generally less dense than solids, and then liquids are in between. The atoms are closer together, but not as close as a solid. So they move more freely, but not as freely as gases. Now, soluble compounds are called aqueous. It means it's that substance with water. Okay, they look like liquids. If something is aqueous, it's wet just like a liquid, but it's not pure. Liquid water is pure, but if you dump salt in it, you've created salt water. So that's an aqueous solution of salt and water. Okay, so that's what it means to be aqueous. Now, again, this is for ionic compounds only. Now, this part right here is what we will use to predict products. So these solubility rules are for products only. The state of matter is what I'm telling you. So what I'm saying is how do you know your reactant state of matter? The wording and the problem will tell you. Okay? This chart right here is only used to predict the state of matter of products. Okay? And again, it's going to make more sense when we start practicing. All right? So things that are soluble are aqueous. Now, if you're an exception, it means you're not aqueous. An exception would then be solid state of matter, also known as a precipitate. And we're going to get more into this. So what this means is if you see anything with nitrate as a product, it will always be aqueous. There are no exceptions. So like sodium nitrate, lithium nitrate, potassium nitrate, calcium nitrate, magnesium nitrate, copper nitrate, whatever. Any nitrates are soluble. They are always aqueous as products and no exceptions. Okay? Chlorides are generally soluble, like sodium chloride, lithium chloride, potassium chloride. They're generally soluble, so aqueous. But if you end up with like lead chloride, so like this guy, this is a chloride that is not soluble in solution, making it a solid. So all the guys over here are solids. They're exceptions to being soluble, making them insoluble. These are known as precipitates. Okay, if something is insoluble as a product, it's called a precipitate, and we'll go into that more too. Okay, so then you notice that this is separated by soluble and insoluble compounds. So all of these guys as products tend to be insoluble. Insoluble means solid, not soluble, solid. Which means the opposite is true for their exceptions. Their exceptions are then aqueous. So like calcium dichromate is a solid, but sodium, because it's an alkali metal, dichromate would be aqueous. Okay, so we're just going to practice on learning how to read these based on reactions. Again, we're going to practice this a lot. So if you don't feel comfortable with it yet, it's okay. We're going to do tons of practice. So we're going to, right now, do practice when we're going to assume these are all products. Okay, that these are products that have been formed from, a chemical reaction. So these are all products that have been formed from a chemical reaction. And we're going to predict their solubility, okay? If it is soluble, remember soluble means aqueous, we're going to circle it. And then if it's not soluble, we're just not going to circle it. So let's do the first row together, okay? Silver chloride. So you go to your solubility rules. Okay, silver chloride. Just as a reference, there's tons of ions on here. The majority of them are anions, aka negative ions. And then right up here you have your alkali metals, because here's the thing. Alkali metals, who are your alkali metals? Alkali metals are anybody in this first family, and we don't count hydrogen because it's not really a metal. So lithium down, they are always soluble, always aqueous. Other than that, the majority of your solubility rules is anions. So when I say silver chloride, I'm going to focus on the chloride, right? That's AgCl. That's who I'm focusing on right now. Chloride is soluble, right? Unless it's with who? Silver. Is that right? So silver chloride is not soluble. That would make it a solid. So I'm not going to circle that one. Okay? Next, magnesium sulfide. So again, I'm going to focus on the sulfide, okay? So you go back to your reference sheet. Find sulfide. They're down here. See sulfides down here? Here it is. And it's with who? Magnesium, right? So sulfides are not soluble, aka solid, unless they're with an alkali metal or ammonium. Now, you got to be careful. Magnesium is an alkaline earth metal. It is not an alkali metal. So this stays insoluble. It's a sulfide. It's not with one of these. It's with magnesium, not an alkali metal. It's an alkaline earth metal. So this stays solid. So I can't circle that one either. Okay? Potassium carbonate. Now, you will start to get good at this. Potassium is an alkali metal. Look, right here, alkali metal. What did I just say about alkali metals? No matter what, as products, they are always soluble, always, 100% of the time. There's no exceptions. So the second you see an alkali metal, anybody in this family is an alkali metal, it's aqueous. As a product only, okay? So I'm going to circle it because it's soluble, because alkali metals are always soluble. Okay? Copper 2 sulfate. So I'm going to focus on the sulfate. So here's sulfate. Sulfate. Soluble, aqueous, unless it's with lead or silver or barium or strontium. It's not right now. It's with copper, right? So it's soluble. It stays soluble, aqueous. So I'm going to circle that one. Oops. I should. Okay, hold on one second. Sorry. That is not. Oops. This is not circled. I was just circling the anion. This will be circled for sure. I'm going to skip this one for a second, okay? All right. Iron 3 hydroxide. So let's find our hydroxides on our solubility rules. Hydroxides. Ooh, they're down here. They are not soluble unless they're with an alkali metal or any of these. Well, in that question, it's with iron. I don't see iron over here, so we're still stuck over here. Insoluble. It's a solid, so I'm not going to circle it. Okay. Lead 2 sulfate. So let's find my sulfates. Here they are again. They are generally soluble, but not when they're with lead. So this is a solid. I'm not going to circle it. Okay. Barium hydroxide. So here's my hydroxides. They are not soluble generally. But barium is an exception. So that will be soluble. So I'm going to circle it. I'd like you to try to finish the rest with your solubility rules. So these should have been the only two that you picked. Ammonium is always soluble, and acetate is also always soluble. Phosphates are insoluble, and magnesium is not an exception. And sulfides are also insoluble, and copper is not an exception. So, okay, so what we're going to start doing is we're going to start taking chemical reactions, which we've already done, like single replacement, double replacement, combustion, what am I missing? Synthesis, decomposition, and we're going to start doing what are called net ionic equations. The only thing you can break apart into ions, that's what ionic means, are things that are termed aqueous, that have the state of matter of aqueous. You cannot touch solids, you cannot touch liquids, you cannot touch gases. They stay the same. You don't mess with them, okay? Now, we're not going to get so far into this in this class, but you can't only be aqueous. So two things have to be true if you are aqueous, okay? So one, you have to be aqueous, but two, you also have to be a strong electrolyte or a strong species. So that means all of our salts, ionic compounds, as well as our strong acids and our strong bases. So what this also means is that, like, acetic acid is not a strong acid. It's a weak acid, but it's aqueous. Because it's not a strong acid, just even though it's aqueous, you would not get to break it apart into charged species, okay? And we aren't going to get much into that in here, but that's what the other criteria is. So again, the only things that we're going to rip apart, so we're going to take compounds that we put together and we're going to rip them back apart. They have to be aqueous. What will you do with solids, liquids, and gases? Nothing. You will rewrite them as they are, completely unchanged. Okay, so we're going to do some practice. All right, here we go. Let's do a really big flashback. So write this reaction down.
One quick question. Did we have to write the net ionic equation rules?
No.
Like, do we have to write that down?
Nope. So now let's see how much you remember from January. Please try to predict the products. So the first thing you want to do is classify what kind of reaction it looks like. Plus, minus, two compounds, right? Probably going to be a double replacement, so they're going to switch partners. So the lead is going to go with the iodide. So yes, you will still have to be able to do this in this chapter. So +1, -1. Now lead is +2, and its new partner is iodide, which is -1. So I need 2 of the iodides to balance out the +2 charge. So plus Pb, and I need 2 iodines. What's next? You got to balance, right? So I have 2 nitrates, so I need to put a 2 here to give me 2 nitrates. That gives me 2 sodiums, so I have to put a 2 here to give me 2 sodiums. That gives me 2 iodides, which works out nicely because there's 2 over there. So it's been a while. You definitely want to get back in the swing of this because this is the bulk of the rest of the chapter. So now, what does this mean, lead 2 nitrate and sodium iodide? Well, I'm about to show you. So you look at my screen. I literally have a container of lead 2 nitrate. It looks like water, and it's not. It's lead 2 nitrate dissolved in water. Yeah? What state of matter should we call this? Is it liquid? It is a liquid, but is it liquids are pure? Is this pure? No, because there's lead 2 nitrate with the water, right? So we call that aqueous. This is an aqueous solution of lead 2 nitrate. So let's go back. Aqueous, state of matter. Okay, now I have sodium iodide. Here it is. Also looks like a liquid, but it's not. It's sodium iodide. So it's sodium iodide with water. I took solid sodium iodide, I dumped it in water, and I stirred it around, and now I have a solution of it. So what state of matter is this? Aqueous. Okay, so let's go back, call this aqueous. Okay, now I told you we use our solubility rules to predict the states of matter of products that are ionic. Okay, so we're going to use our solubility rules to look at sodium nitrate as well as lead 2 iodide. So let's pull them up. So sodium nitrate. Let's get rid of all this. Now you can look at this two ways. In my AP class, I basically make them remember that nitrates are always soluble, always, as a product, 100% of the time. There's no exceptions. I don't see anything written over here. So if you see a nitrate as a product, it's always soluble. But it's also like a double whammy because alkali metals are also always soluble. So like this thing is legit soluble. What state of matter does that mean? It's aqueous. So I'm going to write aqueous. Okay. Lead 2 iodide. Again, we're trying to focus on the negative part, the second thing, the iodide. Those are the easier things to find on the solubility rules. So here we go. Here are my iodides, I minus. They're generally soluble, but not with lead. So what do I put? If it's not soluble, it's insoluble. That makes it a what? Solid. This has a name, and you need to be very familiar with it. It's called precipitate. If I am telling you right now that I'm about to take 2 aqueous solutions and I'm going to end up with a solid, right? That sounds like magic, right? But it's not. It's chemistry, okay? A solid is going to form from the reaction of these two things together. This isn't solid and this isn't solid, yet I'm going to get a solid, okay? So, are you ready? Let me put my goggles on for safety reasons. I always thought goggles were bad until I had to wear goggles with a mask. Then that's extra bad. Okay. So I got a test tube. Okay, there's nothing in it. And then I have these 2 different pipettes. Why do you suppose I'm using 2 different pipettes? You don't want to put one in one and then put one in another, right? That would cause contamination because they're 2 different substances. So one is for the potassium nitrate and one is for the sodium iodide. Which one do you want me to throw in the test tube first? Okay, sodium iodide, sure. Okay, so I'm going to take it. I have this little thing that I can suck up the liquid with, maybe. Okay. And this is very qualitative. I'm not measuring an exact amount. I'm just using this to dispense it in there. Solution, right? Okay. That's the sodium iodide. I'm going to put its thing off to the side. All right, now I got my lead 2 nitrate right here. Right? Oh no! Make sure it's always in tight. I'm going to pull some of it out of here. All right. You should be able to tell that this is definitely a solution, right? Like, this is not a solution anymore, right? Like, I know it looks like liquid still, but if I let it settle, you're going to see solid at the bottom. Like, you can't see through it, right? So you know there's solid floating around in there, right? A precipitate was formed, and actually it's a yellow precipitate, which is pretty cool, huh? I mean, minus the fact that it has lead in it, but right, because lead's poisonous. Okay, but right, this is totally a solid. There's solid in here. So as class goes on, we're going to do some more practice. I'm going to let this sit, and you'll be able to see the solid will eventually settle out to the bottom because solids are generally more dense than anything that's aqueous or liquid. And you'll see the yellow solid on the bottom and the other part on the top. Okay? So for sure a reaction happened. Like, this looks nothing like what we started with at the beginning, yeah? I didn't like pour any magic dye in here. This is a precipitate was formed from two aqueous solutions. Okay? So now what has to happen is we have to discuss what actually happened. And that's where the net ionic comes into play. Okay, so that's what we need to do. Is we're going to start doing what's called a net ionic equation. So I'm going to go back to my reaction, please. Okay. This part of my reaction, and you please make note of this, this right here, this whole reaction is called my molecular equation. It's the normal one that you're used to. This is not unfamiliar to you, but what we're about to do will be new, okay? So when I say lead 2 nitrate aqueous, what it means is lead 2 nitrate is not just stuck together as lead 2 nitrate inside of this container. What it means is if this is aqueous, I have lead ions floating around in this container, and I have nitrate ions floating around in this container. That's what it means to be aqueous. Okay, so when I say sodium iodide aqueous, it's really sodium ions floating around in here and iodide. It's not solid, intact sodium iodide. There's no solid in here, all right? These are ion forms. So anything that's aqueous, we have to break apart into ions. So we do the exact opposite of us putting them together. So we put them together to form compounds. Now, if they're aqueous, though, we're going to rip them back apart into their individually charged particles. So what does that mean? What does that look like? Lead 2 nitrate is aqueous. So I'm going to rip it apart into its ions. So which ions made lead 2 nitrate? Well, lead, right? Solid lead? No, this is lead ion. Aqueous means ion. And nitrate, right? But there are how many of them? Two nitrates. I'm taking this compound and I'm ripping it back apart because that's what it means to be aqueous. Okay, so now I have to do that for this other aqueous species. This is aqueous, right? So I go plus. How many? So this is sodium ion, right? Na plus 1. But don't forget, you got to distribute that 2 out in front, okay? There's 2 of them. And there's also 2 iodide ions. Okay, keep going. Arrow is what's next. I'm just reading across. This is aqueous, which means it's solution form. So it's ion form. So I rip it apart. Na plus 1, and there's 2 of them, and 2 nitrates. So nitrate is NO3 minus 1, and there's 2 of them because of the coefficient. Now, what are the rules for something that's not aqueous? Do I get to do anything to it? No, you have to leave it alone. You do not get to touch solids, liquids, gases, ever, ever, ever. So you rewrite it as it is. So I'm going to write PbI2. This right here, what we just did, is called your gross ionic equation. Gross because we've ripped apart everything that's aqueous that we could. So now we have to cross off things that are the same on both sides. So can you see one ion?
Sodium nitrate.
Okay, well, there's both of them. So there are two nitrates on the reactant side and there are two nitrates on the product side. So we're going to cross them off. And there's two sodiums on the reactant side and two sodium ions on the product side, so we cross them off. And now what we have is called our net ionic equation. Net is what's left over. So now I'm going to write out everything that I have left. And I'm going to go back and include my states of matter. All ions are aqueous. All ions are aqueous. So this is my net ionic equation. The things that I crossed off have a name. They're called spectator ions. And the reason they're called spectator ions, like a spectator at a sporting event is someone who is not in part of the sporting event, they're just watching. And this is the same thing in a chemical reaction. These ions are in there, but they're actually not doing anything. They're just floating around minding their own business. The only two ions in this instance causing the reaction are the lead and the iodide. The sodium and the nitrate do nothing. They just sit in there and mind their own business. They do literally zero things. It's really these two ions forming the precipitate that cause the reaction. Okay? So let me reiterate. You must put charges for things that are aqueous or it's not correct. You don't put charges for anything that is solid or liquid or gas. You just rewrite them as they are. You don't change anything about them. Okay? So we're going to try to do another one. Now, the first thing I'd like you to do is we're going to practice predicting the products of the reaction. So let's see, who should I do next? So I would like you to please take a moment to predict the products and then balance your reaction. Any questions on predicting the products? This is plus, nitrate is -1, so that made the copper +2. Hydroxide is -1, sodium's +1. So the copper pluses and minuses are what go together, remember. Okay, now I'm going to show you my reactants. You ready?
One quick question.
Yep.
Yeah, is the copper nitrate insoluble?
No, well, I'm going to go, the reactants I have to tell you, and the solubility rules are for products only. So we're going to use the solubility rules for these guys over here. But I'm going to start with my reactants first, okay?
Okay.
All right, so Copper 2 nitrate is this. It's kind of pretty, huh? It's blue, but it's a solution, right? I don't know if you can tell at home, but like it's you can see through it. It's transparent. Like you can totally see through it. It is blue, but it's a blue colored salt solution. It's really, really pretty. Okay, so copper 2 nitrate. What state of matter does this look like? Aqueous. It's a liquid, but it can't be a liquid because it's not pure water, right? So we call it aqueous, right? So this is an aqueous solution of copper 2 nitrate. So let's put that. So this is aqueous. And then I'm going to use sodium hydroxide, which is this. Looks like water. It's not water. Sodium hydroxide. Okay? Sodium hydroxide. So what state of matter is this? If it's not pure water, it can't be a liquid for now. So if it's sodium hydroxide with water, it's aqueous. Okay? All of these solutions that have things in them are aqueous. So let's go back into aqueous. Now you need to use your solubility rules to predict the state of matter of your products. So if you remember, nitrates are always soluble. Always, 100% of the time as products. So you write aqueous. Nitrates are always soluble. Let's try to figure out copper 2 hydroxide. So we go on here, and I see under the insoluble compounds that hydroxides fall under there. Copper 2 hydroxide, and copper's not an exception, so we're going to remain insoluble. What state of matter do we write if something is insoluble? Solid. Very good. So we're going to write this as a solid. So basically, a what is going to form from this reaction? What is this called? This is called a precipitate. So again, we have our, let's see, what color should I do? This is our molecular equation. Okay, let's do our gross ionic equation. And on some of the worksheets, you're going to see this abbreviated gross ionic equation, okay? That means we break apart everything into ions that is aqueous. So I'm going to rip my copper 2 nitrate back apart into its respective ions, which are copper 2 plus and nitrate, but there's 2 nitrates, so the 2 comes out front here. This 2 goes out in front. And sodium hydroxide is aqueous, so I'm going to rip it apart into its ions, so Na plus 1, but there's 2 of them, and 2 hydroxides. Hydroxide is minus 1, and there's 2 of them. And I'm going to write my arrow. Arrow. I do not get to touch solids. You have to just rewrite it as it is. So CuOH2. Now this is aqueous again, so I have to rip it apart. Na plus, and there's 2 of them, and 2 nitrates. Nitrate, and there's 2 of them. So this is called my gross ionic equation. My net ionic equation, which will be abbreviated NIE, net ionic equation, we will have crossed off our spectator ions. Those are the things, the ions that are identical on both sides. They have to be present on both sides in the same amounts for you to cross them off. So 2 nitrates as a reactant, 2 nitrates as a product. 2 sodiums, 2 sodium ions. And now we write what is left over. That's what the net ionic is. So it's like, in terms of like money, When you get paid, your gross income is how much you make, and your net income is how much you make after the government takes all your money in taxes. Net's like what's left over, what you get. Okay, so I'm going to write it, and you tell me if this is right. No, what's wrong? I forgot the charges. You can't just like say, see your charges. Okay, what state of matter are all charged particles? Aqueous. All charged particles are aqueous. And then this guy was my precipitate, so it's a solid. So this is my net ionic equation. So what does that mean? It means when the copper comes into contact with the hydroxide, a solid is formed. So what are the sodium and the nitrate doing? Nothing. They're literally doing nothing. They're just sitting there watching the copper and the hydrate hook up, or hydroxide hook up. They're not participating in the chemical reaction. Just like spectators at an event do not participate in the event. They're just watching. Okay? That's why they call them spectator ions. So I'm going to do it though. Okay? So I'm going to stop my share real quick so you can see better. I got a test tube. I got all my goggles, right?
I got a question. I'm just wondering, like, why are the copper and hydroxide connected together?
Because they have limited solubility in solution. Okay, so I'm going to put this in here. Now, again, I realize this has color. I realize it's blue, but you should totally be able to tell that it's transparent. You can see through it, okay? There's nothing like floating around in here. There's no solid. It's just a colored species. And then again, I have my sodium hydroxide. Definitely, this is colorless. This definitely doesn't have color. By the way, we don't call these white. We call them colorless. We don't even call them clear. They're called colorless, okay? And I'm going to put it in here. You ready? Should a solid form? Based on we just predicted a solid should form, right? So hopefully one does. Otherwise, our solubility rules suck, yeah? So let's go. Oop. It's actually kind of stuck in there. Nice and, ooh, that's not going to work. Chunky. Let me get a stirring rod, okay? But you can definitely see that there's a solid kind of stuck up at the top now. And that solid is who? It's copper 2 hydroxide. Let me get a stirring rod and try to stir this a little bit. So now that I kind of messed with it, you can tell you cannot even see through this anymore because there's solid particles floating around in here. And let's see. Let me add some more. I mean, you can just see every time I add it that more solid is formed. Okay? And again, I'll let it settle out, but a precipitate is formed here. They're not two transparent solutions anymore. I can't even see through the test tube because of the precipitate that's formed. You can kind of see the yellow isn't completely gone yet. It will be by the next time I see you guys. But you can see the solid forming in the bottom. And it will eventually all settle out, and the solid will sit here, and then you'll have the colorless solution up here, back up here. Okay? And then the same with this one. All right? Okay? Reacting with means plus sign. Magnesium. Magnesium. You go on your periodic table. It's an alkaline earth metal. This is my +2 family right here. Chloride is Cl, and you go to your periodic table. It's -1 family right here. So when you put them together, you get MgCl2. Oh, and it says solution, so I'm going to write aqueous. Now, you need to predict the products, right? So this is another classic double replacement reaction where the silver is going to hook up with the chloride and the magnesium is going to hook up with the nitrate. Make sure you reconsider their charges though. If silver is +1 and chlorine is -1, they go together perfectly. Magnesium is +2. Nitrate is -1. So I need 2 nitrates to balance it out. Again, this is old stuff. Now, you will use your solubility rules to predict the states of matter of our products. So let's pull that up. So chloride and silver chloride, generally soluble, but not with silver, so insoluble. That makes it a solid, also known as a precipitate. Okay? Nitrates as products are always soluble, every single time. So the second you see a nitrate on the product side, you just write aqueous. Where is that? If you look on your solubility rules, nitrates are soluble and there's no exceptions. Always soluble 100% of the time. So I would like to give you a moment to balance and then do the net ionic, please. Try to do it this one on your own. Sorry, I kind of ran out of room. So it ends up being 2 silver ion, 2 chloride ion to make 2 silver chloride. Again, ions are always aqueous. And then this is a precipitate. You can reduce that though, since everything is 2, 2, 2. You could divide everything by 2 to make it 1, 1, 1. 1 silver ion, 1 chloride ion to make silver chloride. So again, what are the magnesium and the nitrate doing in solution? Well, nothing. They're just sitting in there floating around. If you'll notice, this is, sorry, it has like a sticker on it, but it's magnesium chloride. It says aqueous solution. It's colorless too, aqueous, right? Okay. And then this is silver nitrate. Silver kind of stains, which is why the bottle looks like this, but this is totally an aqueous solution right here. Okay. So I'm going to dump some in here, or squeeze some in here. All right. Oh, of course it goes drop by drop. Okay. That's the silver nitrate. Okay. This is the magnesium chloride. Oh boy, it's stuck. Some more for fun. And the lead to iodide precipitate is yellow. This one's silver chloride is white. It's a white precipitate. Can I see it in there? Okay. And then you go ahead and try to do your complete ionic equation as well as your net ionic equation. Complete and gross mean the same thing. So, right, it's helpful to do this, like to assign the charges when you're predicting products. It's helpful for when you switch them, right? The plus is going to go with the minus, and the plus is going to go with the minus. It is standard practice to write the cation, the positively charged ion, first, if you haven't noticed. So I'll give you a couple minutes, maybe like 4 minutes since class is almost over. So the hard part of this one, I don't know that it's hard necessarily, is that every single thing is aqueous. Sodium chloride is considered aqueous, which means everything breaks apart, right? So here's my molecular, here's my gross, here's my net ionic. So we cancel everything out that is the same on both sides, right? So look, 2 sodiums, 2 sodiums, 2 nitrates, 2 magnesiums. Oh boy, there's literally nothing left. What does this mean? Just because you put 2 things together doesn't mean a reaction will always occur. If everything in your reaction ends up being aqueous, there's no reaction. Literally nothing's going to happen. Basically, they're just going to mix together. So just because you throw 2 different chemicals together does not ensure a chemical reaction. Okay? So watch, I'm going to show you. It's the most boring one we've done today. I got my test tube. Where's my magnesium chloride? So here's my magnesium chloride again, right? Solution, aqueous, transparent solution, colorless. Here's my sodium nitrate. I got a big, huge container of it. Also colorless, okay? Transparent solution. So this is my sodium nitrate. Okay. And then I'm going to take it, I'm going to add my magnesium chloride. Wah, wah. Literally nothing's happening. I mean, I have more stuff in here now, but there's no reaction. They just mix. They don't react. So not every single combination of chemicals produces a chemical reaction. Some things don't react together. So it's still, they're both just transparent solutions. Now, I'm going to tell you something. I'm going to add another thing to this. Copper 2 nitrate. Copper 2 nitrate, ooh, actually that'll be okay. Nitrates are always soluble in solution, is that right? Okay, so if I put this in here, let's see what happens. Nothing happens. Now, I understand that it did turn blue, right? But that's because this is blue. So if you put something in blue and something that's colorless, it's going to turn blue, right? But do you see any solid in here? No. Do you see anything? Do you see bubbles? Nothing, right? So no reaction still. Just because something changes color does not always indicate a reaction either. So I want to make that clear. Okay, so your homework over the weekend and tonight and tomorrow is going to be to do these practices. I haven't put them up yet, but you're going to doing practice net ionic reactions. Okay.